In many situations, we need to demonstrate validity of assertions. For example, you are a venture capitalist and is proposed a project running 36 months. With 36 months data at hand, should you invest in this project? Suppose you will invest if average monthly profit is over 20,000. This question is not to ask you to estimate some parameters. Instead, you need to make a judgment whether the condition is satisfied. We need a new statistical tool, hypothesis testing. This is a daily close price of Apple from 2007 to 2018. It looks like the price is in an upward trend, and we may guess the average of daily return is positive. However, if we plot the daily return directly, the daily return goes positive and negative. An assertion that the average of daily return is positive is not obvious. It is also not obvious whether the average of daily return is zero or not. In a histogram of daily return, it is approximately symmetric about zero. It is still not obvious whether the average daily return is different from zero. We want to use a quantitative statistical tool to make judgment about the assertion that the average daily return is not zero. In statistics, hypothesis testing can use sample information to test the validity of conjectures about these parameters. Let's start with hypothesis testing. The first step is to set hypotheses. We have null hypothesis and alternative hypothesis. Usually, the null hypothesis is the assertion we are against. Alternative hypothesis is a conclusion we accept whenever we reject the null. Hence, in our example, the null is population mean. The average daily return is zero. In alternative hypothesis, average daily return is not equal to zero. Whether to reject or not reject null hypothesis is a sample-based decision. Intuitionally, given that the null is correct, the difference between sample statistic x bar and the population parameter mu cannot be very large. If it is significantly large, the null should be incorrect, and we should accept alternative. To measure the magnitude of difference, we also need to consider the standard deviation of sample, because the sample with large standard deviation, usually this magnitude is larger. Hence, we need to do standardizations. If we know population standard deviation, the standardized sample mean we denote as z hat has a z-distribution if population is normal or sample size is large. If z hat is far away from zero, the null is not likely to be true. In hypothesis testing, we start with assumption that the null is correct. Hence, we know population mean is equal to zero. But in most situations, population standard deviation is not known. Then we can replace population standard deviation with a sample standard deviation. Then this new term, denoted as t hat, has a new distribution, t distribution. Similar to z distribution, t is symmetric with respect to zero and bear-shaped. The difference lies in the tail. T distribution has 5 tails, which implies t has a higher chance to take values in the 2 tails. The t distribution is dependent on the degree of freedom. In our example, the degree of freedom is equal to degree of freedom of sample standard deviation, which is n-1. As sample size increases, degree of freedom increases and t is more and more like z distribution. So, with large sample, we can treat t as if it is a z distribution. We will use a t distribution in next topic. With large sample, t hat follows z distribution. Hence, we denote this statistic using z hat 2 to emphasize that it follows z distribution. We can compute z hat using Python. X bar is sample mean, average data return. S is sample standard deviation. N is sample size. Z hat equal to 2.5897 is a standardized statistics. We use mu equal to 0 because we assume the null is correct at the beginning. If z hat is different from 0 significantly, we can infer that this sample is not sampled from the population with mean equal to 0. Then we can reject the null. How to define the significance level? We use a probability on the two tails of the distribution. We fix this significance level, for example, alpha equal to 5%, which is the probability for z to take values on some domains of the two tails. We can see that these two domains is z less than negative 1.96 and z bigger than 1.96. Negative 1.96 and positive 1.96 are 2.5% and 97.5% quantiles of z. These two domains are called rejection region, and this kind of test is called two-tail test. If statistic z hat falls into rejection region, we can tell that statistics is far away from 0 significantly, and then we can reject the null. Here, we should notice that z hat is also possible to take values in rejection region, even if the null is correct and mu equal to 0. This chance is equal to alpha, 5%. In other words, we have 5% chance to reject null wrongly. This is called type 1 error, and the probability of type 1 error is identical to the level of significance level. If significance level is small, the probability of type 1 error is smaller. Here, we demonstrate how to get quantiles, which is also called critical values. Alpha equal to 5% is given, hence null.ppf can be applied to get quantiles. In the print, we use a Boolean number to generate whether reject or not directly. Hence, our final conclusion, we will reject null hypothesis, and the average data return is not equal to 0. Our conclusion may be wrong, but it happens only with 5% probability. We may want to further demonstrate that the average return is in fact positive. We need another kind of test, one-tail test. In one-tail test, the null is the average data return is less than or equal to 0, which we are against. In alternative hypothesis, the average data return is positive. First, we take a mu equal to 0. We still need to standardize sample mean, which is the average data return in the sample. If z hat is significantly large, which implies that sample mean is positive, comparing to mu equal to 0. Hence, it is not likely to be sampled from population with mean equal to 0. It is also not likely to be sampled from population with negative mu. Similarly, we fix significance level alpha and identify rejection region using z distribution, which is z hat is larger than z alpha. Using Python, we can show that the null is rejected at 5%. It means that the average data return of population is indeed positive. From this result, we do need quantitative statistical tools to validate our assertion in addition to visualize the data. Conclusion. For population mean, we have these three kinds of hypotheses and rejection criteria. For different kinds of hypotheses, the criterion is different. A more popular way of testing is to compute p-value. We know that given the null is correct, standardized sample mean follows z distribution, What is the probability for this distribution to take a more extreme value than our observation in given sample? This is a p-value. If p is less than alpha, which is the threshold, it means that the null is unlikely to be true. With the p-value, we only need to compare it with alpha, although the way to compute p is different. Here's a demonstration of p-value approach. In two-tailed test, ABS is to compute the absolute value. We use norm.cdf to compute cumulative probability. In this video, we discuss another quantitative tool which is applied to validate assertion about the population. In next topic, we will use all knowledge we learned in topic 2 and 3 to explore relationship among different variables to build a prediction models in stock market, and finally evaluate the performance of our models.